Hi, and welcome back to the course Agricultural and Biosystems Structures Engineering. This is lecture 8, and this is a continuation of the previous lecture on combined loads. Now, our focus on this discussion will be on the simplification of the analysis. Okay, in the previous discussion, the focus was on thin-walled pressure vessels. Okay, because that's a very classic example of uh, a structure, okay, that encounters loads along its axis, okay, along its dimensions, okay, circumferential or hoop stress, and then you have the longitudinal stresses. Now, in general, okay, the discussion on combined loads, okay, dwells on the combination of different loads on a certain structure, okay, or component structure. That would include the axial load, torsional loads, bending. Uh, that would be also broken down into moment, okay, and shear. So you have here a diagram showing such, okay, you have your bending, okay, producing that shear, and then you have the torsional effect as it is bent, and then you have your forces. Now, stress transformation analysis is used to simplify uh, combined loads. And in the succeeding discussion, the topic will be on stress transformation and the determination of the principal stresses and the maximum in-plane shear stress, and likewise the absolute shear stress, which is critical in ductile materials. Now, the simplification of this method leads to the use of the Mohr circle, okay, which we will be discussing in a while. And well, they're actually more complicated, but well, very much useful. Okay, the finite element analysis. It's a finite element method that is used to simplify the computation of. This is a computational technique used to determine the, the the stresses and strains in a certain body. The This is a an extension, okay, of the concepts uh, in this specific concept, and will not be okay. Will be probably just discussed in passing. Okay. Now, previously there was an example on a farm sign, okay, and it was solved, okay, well, because the given are in the variables, okay, acting on the variables defined as variables. So the solution, okay, were in um, variables as well. Okay, so you have the following diagram, okay, the schematic diagram, okay, the free body diagram showing the forces and the yeah, the forces acting on the body. Uh, well, if we are trying to find for a specific portion, okay, as shown on the screen, so you have here a cross section, okay, particularly this area, okay, that would be a analysis now for structural concern, okay, the structural analysis. So um, let's try to okay, let's try to analyze this cross-sectional portion. So we will be translating the different forces acting on this the diagram on the left. Okay, so we will try to translate this diagram towards this specific diagram showing the cross section of this area. Okay, so uh, we have here the Cartesian coordinate, the XYZ system. And so we have the tendency for the body to rotate, okay, or to bend. Okay, so there's torsional, there's moment. Okay, so you have here a moment about z. Okay, this is the z-axis, and a moment about the y. So this is the y-axis. So we have a moment about y, and then we have as well along, okay, along x. Okay, we have a torsional tx, and then so is there an x along x? Is there a moment about x? There's none. Okay, so you have here the weight of the body. So the weight is actually the weight of the steel and the weight of uh, the mast. Okay, so it's going to be weight of the mast at x equals to negative h. Okay, because you have to cut off the remaining portion. Okay, this is a certain height. This is of supposedly a certain height h. Okay. Oh, sorry. That should be from a certain height h. Okay. H. Now, the other, okay, the only remaining well, effect or force that is exerted by the wind is this shearing effect, okay, which is actually the force of the wind. It would depend on the location, okay, and then we will be proceeding on. We will be proceeding from this and the analysis of this, because we're going to analyze specific portions of this steel structure, okay, from this side. For example, this is the YZ, no, this is the XZ plane, and another portion here, right? And this is, we are going to talk about a very infinitesimally small portion of this structure again. And this is on this side is the XY plane, okay? So if you're going to look at this side, the structure is going to experience a different, okay, a different set of forces with respect or against this side, okay, the XY plane and the XZ plane. Again, we are going to generalize the stresses into either into both or to a normal stress and then shear stress. So let's try to simplify that. We have, okay, for the plane XZ, we have sigma, okay, or yeah, that's the normal stress, ZX or XZ. You have the force, okay, it's going to be negative W over A. It's going to, this is the area, right? And then you have a minus of the M times the Z times the R, okay? What's the R? It's the radius, okay? So it's going to be affecting this portion along that the area will be affected by a moment about this this direction, right? So it's about a radius R, and it's going to be over I Z. Later we'll define these variables. Your shear is equal to, okay, it's very simple. It's just the Tx times the R again, the radius over the J, okay, the torsional moment. Okay, so next is the xy. Okay, take note of the difference in the equation. We still have the W, a -1 going down, right, over the area, but we have a plus. And okay, the MC will have no effect because it's along a different plane, but the the my, okay, the moment about the y will have a great effect, or such an effect that it has to be considered, okay, and you have your IY. Okay, You have your shear this time. It's t negative tx. Okay. Why? Because it's along this line. Okay. We have a notion that uh, this is going to be a positive. Okay. But this is going to be a negative. So this is a negative. Okay. And it's going to be still times r over j, but we add a the shear, okay, over a. Actually, here, okay, in the shear, we can consider a certain factor, okay, concentration factor, CS, but it's actually negligible. So see the difference, right? Take note of the difference. This is solvable, but again, the given are uh, in variables. So this will be the final solution for this. You are going to look at this different portions of the structure. Now, if you go about, okay, going about this direction, okay, you will have a different angular uh, stresses, okay, of the normal and the shear, and they will be of a different factor. But okay, just to show here that the different surfaces of the structure will have different stresses, okay? And it is important to take note at which point will be the material be failing. Now, if we have a structure, okay, that we simplify now the transformation of the stress, because we could transform these stresses, okay, and well, we can look at it at the same apples to apples comparison. That's the concept of stress transformation. So let's try to take a look at the concept of the transformation of stress when we're looking at a certain body. And okay, let's try to uh, okay, let's try to see what happens to the body if it is uh, subjected to stresses along different dimensions. So here we have a three-dimensional body that has stresses along its x, y, or along its all three dimensions of the Cartesian coordinate system, and as well as the a shear, okay, in both normal stress and shear stress. So this side is going to experience a stress along this dimension, this one along that dimension, and you have expectedly a different or a a an equivalent opposite stress along this dimension. We try to simplify this. Right? So by looking at the dimension only of one direction, and if we were talking a while ago of the transformation of the stress, okay, along a different location in the uh, round bar a while ago, the mass that we were talking about. What if, okay, we just transform that to a certain direction, okay? Because we have here the original, right? So we have the original XY dimension over here, right? Now, what if we try to, okay, rotate the element, okay? This element is rotated about a certain degree, okay, from the original, because we have here the original, right? The original X and the original Y, and we have a rotation, okay, that transforms the stress to this along this direction. So we can say that this is actually, okay, this is now the normal stress along x prime, and this is the normal stress along y prime. And we have the same shear stress, okay, experienced by this body. Similarly, these are the same shear stress, right? Um, Okay, sorry. We have to. This is just the same, right? X, and this is going to be y prime, and this is x prime. We can, by virtue of the relationship of this body, because we know the delta, or the angle delta, so we can transform this by trigonometric relations. Okay, please take note of this transformation. X, this is going to be a lengthy process. We look at the different properties of the different component stresses, and this becomes, okay, cosine squared theta. Okay, y. We're looking at the original y. Okay, the delta y over here and the delta x along these dimensions, and we're transforming it to a different coordinate system, right? So this is going to become sine squared theta plus 2 the shear, okay, sine theta cosine theta, and the shear, okay, on the other hand, okay, because of the shift in the angle, okay, this will become, this is correct, right? This is correct, right? So sine theta cosine theta plus x y cosine squared theta minus sine squared theta. There's a different y. Okay, the y is going to become, okay, this one. Okay, you take out of relationships. Okay, similarly, it's going to be just it will have a similar relationship to the first stress, okay, normal stress along the x prime. So it's minus. It's going to be a minus. We're talking of the original stress here, okay, and the new, okay, the new. Sorry, this is going to be theta. All right, let's try to simplify this one. Okay, the final stress will become this one, right? So plus, okay, x minus over 2 cosine 2 theta plus xy sine 2 theta, and you have the y prime, okay, again a similar but opposite equation as the first one, cosine 2 theta plus or minus, okay, whether it's minus sure x sine 2 theta, and you have the shear prime xy, okay, sorry, x prime y prime, that's x minus 2y sigma y over 2, the quantity over 2 times sine 2 theta, and you have xy cosine 2 theta. We can simplify this further so that, okay, we get, okay, the maximum value for this one. So yeah, this one. This will get the maximum values, okay, this sigma 2, sigma 1, sigma 1 and sigma 2, which are the principal stresses. And we get here a value of, okay, the shear max, okay, the max in plane, okay, the maximum in plane shear stress, and we have it in this manner, right? Let's try to clear this up. Right, so these are now the, okay, by simplification, okay, the previous equations, okay, is used to determine an arbitrary value for your maximum or your stresses, okay, your stresses in a different angular direction from the original. But you have your principal stresses, and this is our in the maximum normal stresses that the body will encounter. Okay, okay. So you have the normal stresses and the shear stresses computed for a body or the stresses. But when you combine them together, okay, you get your principal stresses, which are actually bigger than your normal stresses computed. And you have also your maximum in-plane shear stress. And later, you still have your absolute maximum shear stress, which is used for ductile materials. Okay, so the principal stresses the equations for them, okay, is as shown. You have your sigma 1 and sigma 2, which means you have your two principal stresses. And later in the Mohr's, this can be more understood based on a diagram. Okay, and you have your maximum in-plane shear stress. Okay, simplified. Now, the average or the values is actually just the sigma average plus or minus the shear max. And shear max is actually the sigma 1 minus sigma 2 all over 2. Okay. Now in when you have your principal stress, actually the body is experiencing zero shear stress. But when it's in the maximum shear stress, okay, the body is actually, or the portion is actually in experiencing the average of the maximum stresses. And you have your the angle of incidence of this stresses as shown. Okay, so use this formulae when trying to solve for the principal and maximum in-plane shear stress using or analytically. But graphically, again, there is a solution, and it's called the Mohr stress. Okay, the Mohr stress will solve the for the principal and maximum in-plane shear stresses using a graphical method. Again, the Mohr circle is a graphical solution. It's actually a tool developed by a German engineer by the name of Otto Mohr, and it relies on the relationships of the different stresses that a body, a portion of a body, or a infinitesimally small portion of a body experiences, okay, when it is transformed in a certain direction, okay, or angular reorientation, transformation. The solution is hereby presented. Okay, you have to first construct a Cartesian coordinate system, okay, where the x-axis will be the location for your normal stress, and the y-axis, okay, for the shear stress. Now the stress coordinates should be plotted in that Cartesian coordinate system, and that should represent the normal stresses and the normal and shear stresses accordingly. Okay, the along the x partnered with the negative of the shear, and the y along the the normal stress along the y-axis partnered with the positive shear, and a line is constructed, okay, between this coordinates, okay, because that would the coordinates already part of a circle, and when you have the coordinates constructed or determined, so you have the endpoints of the circle, then that would now become the line, okay, that's circumscribed by the circuit. Okay, so 2r is now the twice of the radius. Okay, the radius is actually the shear max. Okay, or the twice of the shear max, and it's the diameter of the Mohr circle. Okay, and it intersects the axis of the normal stress. Okay, and at the center is the normal, the average for the the average normal stress or principal stress. And you construct now the circle, okay, so that the principal stresses and maximum in plane shear stress are determined. We will solve. We'll try to look at the an example for this, okay, using the an example from the previous discussion. Okay, so you have the same cylindrical steel water tank with end caps, the radius of which is 24 inches, and the wall thickness. Okay, this is a thin wall pressure vessel because again you have the relationship between the wall thickness, okay, and the radius of the tank, okay, qualifying it as 1. And so you have already the stresses determined, okay, computed accordingly. The circumferential or hoop stress is 12 ksi, and the longitudinal stress is 6 kilopounds per inch or ksi. Now, okay, so we will try to solve for the normals, the principal stresses and the maximum in plane shear stress. Again, this is a very simple solution because the body, okay, a small body here, okay, would be experiencing what, okay, a circumferential stress of 12 ksi, and okay, 12 ksi. Along the longitudinal axis, you have your 6 ksi, okay, and they are both in tension because you have the liquid, okay, or the fluid inside pushing against the bounds of this pressure vessel. Okay, so in actually in other cases you would have your stress probably in tension in one direction, okay, or in opposite directions, and you have your sorry, that's not possible, so you have to erase this one. You have the along another direction, okay, you have compression, okay, and again it's possible that you would have your shear, okay, accordingly. Okay, so you have your shear along here and your normal stresses. This is going to be y, and this is x, and the shear is going to be along your x and y, and you could determine the maximum, okay, in plane shear stress and principal stresses as well when you try to solve for the them using the equations and also the Mohr circle. So let's try to solve this in both the equation and then as well as the both the equation and then the Mohr circle. Okay, so let's solve for the shear stress. No, the principal stresses first. All right, so you have the stress. Okay, it's sorry, why is this black? You have white. We use white. Okay, so the principal stresses are, okay, again the equation. Okay, we just make use of the equation over 2 square. Sorry, we have 2 plus this one with the square root of. Okay, so it's to look at the equation. Okay, since it's actually very long. This is the shear, but this is again 0 in this case because we have 0 shear, right? So it simplifies this equation itself. Okay, this is going to be plus or minus since you have in a square root. Okay, so your first equation, first principal stress will be, okay, this is going to be 12 plus 6 over 2, okay, plus the square root of 12 minus 6 over the quantity 2 squared. So this is going to become what? This is going to become, this is going to be 9, okay, 9 plus 12 minus 6 is 6 divided by 2, 3 squared. That's going to be 9, square root of which is 3. So you get 12 KSI. While your second stress is 12 plus 6K over 2 minus the square root of the same equation from above. Okay, you have to square this first before. So it's actually 9 minus 3, and we get 6 KSI. Well, we get the same stresses actually. Your average is the same. Okay? Oh, no, your average is going to be 12 plus 6 over 2, which is 9. Okay, 9 KSI. Later we'll see it using the relationships, the Mohr circle to show the relationships of these equations. Now, for your shear, right, we get the shear max is square root of 12 plus 6. Oh, sorry, minus 6. Okay, minus 6 over 2. Okay, it's actually this portion of the equation plus 0 shear. Okay, and we get 3 KSI. Let's try to draw the equation, the Mohr circle of this one. Okay, let's use this CAD software. Right? You could use one, then okay, please bear with the use of the different command line codes because you will have to understand what that means. Okay? I'm creating the Cartesian coordinate systems, right? First one is going to be, why is it not locking? Okay, we create an X line and then a V. It's not locking. Why? All right, it's locking now. All right, so that's the first, well, the X line, either the Y, okay, where you have your principal stress, right? The normal stress. And then you have your X, right? So let's try to create a circle first. And so it's going to be what? Offset this one by 6. That's going to be the ends of the circle, the Mohr circle. Sorry, we want to create a circle that has the 2 points identified. So 2P, right? Since we have here the stresses, right? Okay, so you have here the your first stress is 12 KSI, okay, and your second stress is 6 KSI. Okay. All right, let's try to work this back, okay, a bit because we have to create the line first between the circles, right? To create the circle. So we have the coordinates as, okay, we have your shear as 0. So you have your 12 as the first stress, okay, and then you have a 0 shear, and then that's the coordinate number 1. coordinate 1, and then you have a coordinate 2 of the circle that is 6 KSI, and then 0 shear, right? Okay, so this is chord 2. Okay, so to create that coordinates, okay, you have 6 units of this. Okay, you have to offset that with 6 and then 12 actually, right? Because we have the x-axis as the normal stress, right? So this is the 6, right? 6 and 0, okay, and then you have your 12, right? Okay. So we actually have a circle with these points. Circle 2p, this one, right? And we want to create a we have the shear max, okay? We determine now the shear max because we compute already for the principal stresses, and they're just the same. Because why? Because we have just the same values. Okay, we are not moving. Okay, so these are still the principal stresses. We have not moved in a, for example, if we have a circle, okay, okay, if it's going to be in this direction, right? So we could move it a certain location, okay, because of a shear value, okay, from this up, for example. So we have a different principal stress as your normal stress. So that is because we have a zero shear, that we have the same principal stresses as the normal stresses computed initially. But for the maximum in plane shear stress, okay, since we have a zero shear stress, we have an equivalent maximum in plane shear stress. That is what we have computed as 3 KSI, and it is actually, right, it is actually well, it's going to be determined by the topmost, okay, the topmost stress over here, because we have the shear stress along this direction, right? So we just have to measure this value, okay, at what value this is. Okay, we create a tangential line. Snap to the tangential, okay, x line, create a horizontal, and okay, so we get the center of that, right? The center is going to be the average of the two. So the average will be, or the center of the circle will be, okay, we know that this is 6 and this is 12, so we get the midpoint, okay? Next line, we get the midpoint. We intersect the midpoint. Oh, sorry, we get a line between this portion and that portion, and we create an X line that is at the midpoint. Okay, so this is going to be a V, sorry, a vertical line. Okay, this is the midpoint. So we are just going to get the linear distance of this, which is actually just, oh, sorry, there's something wrong. I just delete this one. It's off tangent. Okay? So we have the midpoint, and we get the maximum of the circle, the value of the circle. That's this point. So it's going to be supposedly 3, right? So it's exactly 3. So it's the maximum shear stress that we have, and it's 3 KSI as what we have computed. Okay. So that's how you create the Mohr circle. But in ductile materials, okay, there's a concern because you have the concept of the absolute, okay, the absolute maximum shear stress, which is abs, okay, max. And well, the computation for that is, it's actually just the, if you have your stresses, okay, then the normal stresses, well, if they are both in tension, okay, or in the same direction, so you just divide the bigger stress, right, by 2, and so we have 12 over 2, which is 6 KSI. If it's if the forces are in opposite directions, so you have to subtract the lower stress and then divide this by, or the first, or the principal stresses. Okay, that is the equation supposed to be. Now, how do we draw this diagram? The diagram for this one is actually something like this, right? So create a circle, and we draw a big circle. Now, the shear, absolute maximum shear, is actually this dimension. Okay, so that is 6. That's why we get a 6 KSI value of that. Okay. Now, this is this solution, okay, for this specific problem. There should be a note that if there's a shear, okay, that maximum shear stress is well, the biggest, okay, unlike if you have your purely normal stresses. Okay, so let's go back to the presentation a while ago, and let's focus now on the steps, okay, for the carrying out of stress transformation analysis of combined stresses. Okay, so you determine or compute for the stresses of the critical points, okay, where high stresses are likely, and due to uncertainty of location, usually several points have to be analyzed. And then the Mohr circle for those identified critical points should be determined. And lastly, okay, the relevant stresses should be determined, in particular the normal stresses and the principal stresses of sigma 1 and sigma 2, and the maximum in-plane shear stress. These are for combined normal stresses and shear stresses. But if you have the normal stress purely affecting a body, then the absolute maximum shear stress should be determined. All right, thank you for listening, and I'll see you in the next discussion, which will be on Earth movement.